Okay, so here's question 4. There's no preamble. We dive straight into part A. It says name and outline a mechanism for the reaction of, and then that's an amine. So we should make a note of that. And then we are reacting it with an acyl chloride. And then we are asked to name the amide formed. So they are giving us quite a bit of information there. So it's a 6-mark question. They've said name, outline, name. So let's just make a note of the things that we've got to make sure that we do, so that we can check at the end that we've done these things. So it's 3 parts. They're not necessarily all equal in size, but it's easy to forget to do something in a 6-mark question like this. So I think actually we should start with naming the mechanism, because actually that will help us when we come to outline it. We are talking, we've got an acyl chloride there that featured in our carboxylic acids and derivatives topic, and that only underwent one type of mechanism, and that was nucleophilic addition elimination. So we've got something acting as a nucleophile, something being attacked by the nucleophile. A nucleophile is an electron pair donor. The moment we see a nitrogen, we know nitrogen has a lone pair on it. So the amine is going to be acting as the nucleophile. So that means the reagent being attacked is the acyl chloride, and the part of it that's going to be attacked is the carbonyl group, because that's going to have a delta positive carbon. So let's just draw our acyl chloride. Okay, so it's propanol chloride here, 3 carbons, propanol chloride. It's being attacked by the amine. I think it makes sense to just draw the nucleophile underneath. So yes, a nucleophile is an electron pair donor, so let's put that electron pair there because it's key for the answer. So that lone pair attacks the delta positive carbon in the carbonyl group, and the pi electrons go onto the oxygen. So then we get an intermediate. So remember that the oxygen that the electrons have moved onto is now negatively charged because it's got more electrons than protons. We have to show the pair of electrons that moved onto it. We've still got the chlorine attached. This carbon's now attached to the nitrogen. That nitrogen still has the 2 hydrogens attached to it, and then it has the rest of the alkyl chain as well. So here we've got nitrogen with 4 bonds. Nitrogen typically only forms 3, so essentially for every extra bond it's a positive charge, and that means we've got our negative and a positive, so the overall charge of this species is neutral, which is good because when we looked at the reagents, the overall charge there was neutral, and so whatever the overall charge is, it should be consistent all the way through any reaction. So then we get the next step. So that first step was the addition, all right? So the amine attacking the carbonyl, forming a bond between the carbon and the nitrogen. That is our addition part of the mechanism. The elimination, so we've got the pair of electrons that moved onto the oxygen moving back. So we're reforming the carbonyl bond, or we're reforming the carbonyl group. The electrons in the carbon-chlorine bond go onto the chlorine, and electrons in one of the nitrogen-hydrogen bonds goes onto the nitrogen. And that would be enough to get the marks as far as the mechanism is concerned. But I'm going to draw the product, both because I think if we're doing a walkthrough we may as well, but also because we have to name the amide, and I think drawing the amide is going to make that a lot easier. So always, remember when you're doing condensed formula, it's con. That's how you recognize an amide. So I'm going to draw it with the carbonyl group part first. So CH3, CH2, and then it's the C double bond O. And then the nitrogen is attached to that. It still has one of the hydrogens attached to it, and then it's the rest of its alkyl chain. And then with acyl chlorides, we get hydrogen chloride. Let's just, I think it's useful actually to look at, okay, so that's the acyl chloride, that's what part of the amide that is. The amine is here. So in an amide, you focus, so like with esters, the last part of the name, the ethanoate, was the bit with the carbonyl group. In amides, the bit with the amide part of the name is again also the carbonyl group. So there are 3 carbons in that carbonyl group. So 1, 2, 3. So it's going to be prop. It's all fully saturated. So propan. So the last part of the name is going to be propanamide. And then the second part of the molecule has got 2 carbons as its alkyl chain. So it's ethyl. And that should be joined up. So I'm just going to move that across. And then that ethyl group, we make it clear it's attached to the nitrogen by putting N. So that N-ethyl means that the ethyl is attached to the nitrogen. It's not perhaps necessary in a molecule like this so much, but in sort of more complicated amides, it would be important to make it clear what was attached to the nitrogen, what wasn't. But yeah, so we've got our N-ethyl part of our name, and then we've got the propanamide part of our name. Let's just double check that we have done everything. So we've named the mechanism, we've outlined the mechanism, and we have named the amide. So we have satisfied the 6 marks. Okay. Another 6-mark question. So haloalkanes such as CH3Cl, so chloromethane, are used in organic synthesis. Outline a 3-step synthesis of, and then it's ethanamine, starting from methane. Your first step should involve the formation of CH3Cl. So if it's a 3-step synthesis, we must have 4 chemicals, and they've given us 3 of them, so that's good. It's a 3-step synthesis, and they've told us that we've got to go from methane to chloromethane, and they've also told us that our final step must result in ethylamine. So they've given us essentially 2 of the steps. What else are they saying? So in your answer, identify the product of the second step. So that's the one thing that we don't currently have. That's the one formula we don't currently have, and give the reagents and conditions for each step. So I think we would benefit here from just writing out what exactly they've given us in terms of the formulae and the steps. So they tell us that we start with methane. And it's important, I think, here to think of the homologous series. So it's an alkane. And they tell us that we have to use that to form chloromethane. So that is obviously a haloalkane. Then there's obviously going to be a next step. That will be step 2, but at the moment we don't know what that is. So they've said identify the product of the second step. And then the third step, the final step, results in our final product, our ethylamine. Okay, so that's the information that they've given us, just presented, I think, in a way that makes it much easier for us to, think it through. So before we start doing like step 1, etc., I think it's very important for us to work out what our question mark represents here. Now we are making an amine, so there's 2 ways to make an amine. We can either react a haloalkane with ammonia, or we can reduce a nitrile. And something to think about here, something that should be standing out, is that if we look at the methane and chloromethane, we are looking at 1 carbon. And when we look at our amine or ethylamine, we are looking at 2 carbons. And that, to me, absolutely straight away says that we must have a nitrile as the intermediate. So we must have something with 2 carbons. And this would have been nucleophilic substitution of the haloalkane with the cyanide. And then we would have been substituting that chlorine for a CN, and that's how we've got our 2nd carbon. And so we've got a nitrile here. So you really watch out if you end with an amine, because amines quite often are at the end or near the end of a synthesis reaction. Look and try and see if there has been a change in the number of carbons, and if there has been a change in the number of carbons and it's been near where the amine is in terms of the series of steps, then you're almost certainly looking at a nitrile. And so let's just make that clear that we've now got our 2 carbons. Okay, so we have got step 1, step 2, and step 3. And we've already, by doing what we've just done, we've already identified the product of the 2nd step. Of course, we haven't written that out formally yet. Okay, so step 1. So we are going from an alkane to a haloalkane. So that's free radical substitution. So, and we are substituting a hydrogen with a chlorine. So we must be using chlorine, must be our reagent. Oh, and probably just before I carry on much further, when they say reagent, they mean the name on the bottle. So it's the full chemical name. All right. And then for free radical substitution, the condition, so going right back to the beginning, is you need UV light. Okay. All right, that's good. That's probably 2 marks. Okay, next, step 2. So we're going from our haloalkane to our nitrile. So haloalkanes undergo nucleophilic substitution. So our nucleophile here is going to be the cyanide, the Cn minus. But we have to give the reagent, we have to give the name on the bottle. So we're going to use potassium cyanide. You could get away with sodium cyanide. And then the conditions. Now this is one that's sort of tricky to remember. You need it to be aqueous and alcoholic. And the reason for both of these is to make sure, is to maximize the reaction. Basically, the haloalkane will dissolve better in the alcohol. The potassium cyanide will dissolve better in the aqueous. The alcohol and water will mix together as well. So it just means the reaction is much more efficient. And then the product of step 2, because this is the best place to put it, is our CH3CN, which is ethane. Whoops. Nitrile. Don't forget, this is one of the nitriles are where you actually include the E of the alkane part of the name. So ethane nitrile, as opposed to ethan in most other compounds where it's fully saturated. And then we have to do step 3. So this is where we're going from the nitrile to the amine. That requires a reducing agent. So I'm going to use lithium aluminium hydride. That's a powerful reducing agent. It's in the mark scheme, they're not asking for the solvent here, because actually step 1 has been 2 marks. Step 2 has been 3 marks because it's been reagent, condition, and product. Step 3 here, they just want the reagents, but I'm going to include the dry ether because it's a reminder to us, because there will be questions where we do have to include the dry ether, so just get into the habit of doing. The reason it's dry ether is that water, the lithium aluminium hydride would actually react with the water, so that wouldn't work. So we need it to be in a very dry solvent, or a solvent with no water present, so we use dry ether. And that is our 6 marks. So if you have any queries, let me know.